Hi everyone. This is the 23rd lecture of I-451, Engineering Economy. So we'll continue to solve the end of chapter 6 problem today. And the first problem that we are going to solve is problem 6-31. An engineer has a fluctuating future budget for the maintenance of a particular machine. During each of the first 5 years, $1,000 per year will be budgeted. And then during the second 5 years, the annual budget will be $1,500 per year. In addition, $3,500 will be budgeted for an overhaul of the machine at the end of the fourth year, and another $3,500 for an overhaul at the end of the eighth year. And the engineer asks you to compute the uniform annual expenditure that would be equivalent to these fluctuating amounts. And we are assuming that the interest rate is 6% per year. Okay, so let's visualize the situation that we are currently faced to by drawing the cash flow diagram. So we are working on problem number 6-31. So here we have starting from 0, and during each of the first 5 years, 1, 2, 3, 4, 5, $1,000 per year will be budgeted. So let's say here we have uniform series of $1,000 for the first 5 years. And during the second 5 years, the annual budget will be $1,500 per year. So 6, 7, 8, 9, 10. We have $1,500, right? In addition, it says $3,500 will be budgeted at the end of the fourth year. So we have, let's say, $3,500 at the end of the fourth year, and another $3,500 at the end of the eighth year. So we have $3,500 at the end of the eighth year, right here. Okay? And we want to know the uniform annual expenditure. That would be equivalent to these positive cash flows, right? So basically, we want to know the equivalent uniform annual expenditure for the next 10 years, okay? So we want to know equivalent uniform annual expenditure or equivalent uniform annual cost, okay? So what I'm going to do is convert this positive cash flow to an equivalent present worth at time 0. And then convert this value to an equivalent uniform annual expenditure. Okay? So first, this positive cash flow can be broken into the two components. So the first one include everything but the $1,500 during the second 5 years. Okay, so we have from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have $1,000 during the first 5 years. And then at the end of 4th year, there is $35,000, and at the end of 8th year, another $35,000. Okay, so this is the first component, and the second component is one, 2, 3, 4, 5, 6, 7, 8, 9, 10. So during this, okay, so the second component only contains the $1,500 during the second 5 years. Okay. Okay. So here, the equivalent uniform annual cost can be computed by the present sum of money. Let's say here we have Q sub 0. And here we have R sub 0. So basically, Q sub 0 is the equivalent present sum of money of these positive cash flows. Okay? And R sub 0 is the equivalent present sum of money of this positive cash flow. Okay, so once you get Q0 and R0, you need to combine them together and then convert it to the equivalent uniform annual cost. So you need to multiply by A given P and 6% of interest rate over the 10 years. Okay, so that's what you're going to do now. Okay, so first of all, you need to compute Q sub 0. So how to compute Q sub 0? That is the sum of a uniform series of $1,000 over 5 periods plus these two future sum of $3,500. So here Q sub 0 is $1,000 times P given A, 6% over 5 periods plus future sum of $3,500 at the end of fourth year. So you need to convert it to the equivalent present sum. So you need to multiply by P given F 6% over 4 periods, and another $3,500 at the end of 8th period. So again, you need to convert it to the equivalent present sum. So 3,500 times P given F, 6% over 8 period, right? So let's get these table values. So we are looking at 6% of interest rate. So P given A over 5 periods is 4.212. This is the 4.212. What about this? P given F over 4 periods is 0.7921. What about this? P given F over A period is 0.6274. 0.6274. So how much is this? Okay. We'll get this value later. So now let's compute R sub 0. And we know that R sub 0 is the equivalent present sum of money of this uniform series of $1,500, right, for these 5 periods. So in order to compute R sub 0, first we compute the present worth of this uniform series of $1,500 at the end of period 5. So let's say here we have R sub 5, okay? So we compute R sub 5 and then convert it to R sub 0, okay? So first we're going to compute R sub 5, which is the 1,500 times P given A, 6% over 5 periods, right? So once you get R sub 5, R sub 0 can be computed by R sub 5 times P given F, 6% over 5 periods, okay? And here, P given F, 6% over 5 period is 0.7473. 0.7473. What about this? P given A over 5 periods is 4.212. Okay. So what is the value for this? Q sub 0 plus R sub 0. That's going to be $13,901. And what is the value of this? A given P over 10 periods. That is 0.1359. 0.1359. So how much is this? Okay, it is $1,889. Okay. So here in this problem, what he did is we convert this positive cash flow to an equivalent present worth at time t equals 0, and then convert that value to an equivalent uniform annual expenditure. And in this case, it is $1,889. Okay. Okay. So next problem that you are going to solve is problem 6-33. Okay. There is an annual receipt of money that varies from $100 to $300 in a fixed pattern that repeats forever. If interest rate is 10%, compute the equivalent uniform annual benefit. Also continuing forever. That is equivalent to the fluctuating disbursements. Okay, so we are working on problem number 6-33. So let me redraw the cash flow diagram. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. So n goes to plus infinite. Okay. And at the end of period 1, there's 100. At the end of period 2, 200. At the end of period 3, 300. And then at the end of period 4, 200, and period 500, 200, 300, 200, 100, 200, 300, and 200, and so on. Okay. So if you look at this given cash flow diagram carefully, you may see that a certain pattern repeats infinitely. There is a repeating series of 100, 200, 300, and 200. Okay? So here again, 100, 200, 300, and 200. And then again, we have 100, 200, 300, and 200. And so on. Okay? So, solving this series for A. Which means converting this series to an equivalent uniform series will give us the value of A, okay, which is an equivalent uniform annual benefit for this entire infinite series. So what you are going to do is to solve for this series for A. Okay? So the given problem can be simplified as this, okay? Because these are the repeating series. This pattern repeats infinitely. So we just need to convert this repeating series to an equivalent uniform annual benefit, which will give us the value of A here. And it's going to be the equivalent uniform annual benefit for the infinite series. So here we have A is equal to or first let's break it down to two components. One for the uniform series 0, 1, 2, 3, 4. So take out $100 from each period, and then what is left over? And then the period 2, $100, period 3, $200, and period 4, another $100. Okay? So how would you compute A? A would be simply 100 plus $100 at the end of period 2. So you need to convert it to the equivalent present sum, which is multiplied by P given F and 10% over 2 periods. And there is another 200 at the end of period 3. So plus 10% over 3 periods. Well, let's do this way. Plus the last $100 at the end of period 4. Okay. And then you need to convert this present sum of money to an equivalent uniform series, right? So you need to multiply by A given P, 10% over 4 periods. So if you compute this, then you should be able to get this A value, okay? So you're looking at 10% of interest rate, P given F over periods 2, 3, and 4. So this is 0.8264 and 0.7513, 0.7513, and 0.6830, 0.6830. And then what about this? A given P over 4 periods, 0.3155. Okay. So my computation, this is $195.03. So this is the equivalent uniform annual benefits amount. Okay, and this is problem 6-33. Okay, and next problem is 6-37. Jenny McCarthy is an engineer for a municipal power plant. The plant uses natural gas, which is currently provided from an existing pipeline at an annual cost of $10,000 per year. Jenny is considering a project to construct a new pipeline. The initial cost of the new pipeline would be $35,000, but it would reduce the annual cost to $5,000 per year. Assume an analysis period of 20 years and no service values for either the existing or new pipeline. The interest rate is 6%, then we are required to determine the equivalent uniform annual cost for the new pipeline. And also we need to answer whether the new pipeline should be built or not. I think there is no question mark here. Okay. So the analysis period is 20 years, right? We are working on problem 6-37. The analysis period is 20 years. And for the existing pipeline, the annual cost of $10,000 are required, right, for the next 20 years. So here, starting from 0, 1, 2, and so on, up until 20, the annual cost of $10,000 required. So this is EUAC for existing pipeline. Okay, so let's say is EUAC sub E. And for a new pipeline, initial cost of $35,000 are required. So 0, 1, 2, up to 20, and initial cost of $35,000 are required, but it would reduce the annual cost to $5,000, right? Annual cost of $5,000. And what is the interest rate? Okay, the interest rate is 6%. Okay. So how do you compute equivalent uniform annual cost for the new pipeline? It's going to be 5,000 plus, you need to convert this present sum of $35,000 to the equivalent uniform annual cost. So 35,000 times A given P, 6% over 20 period. Okay. So what is the value of this? 6% A given P over 20 periods is 0.0872. 0.0872. So how much is this? Okay, this is the $8,052. Okay, and the part A asking us to compute the equivalent uniform annual cost for the new pipeline. So this is the answer for part A. Okay. Then how do you answer part B? Should the new pipeline be built? So you need to compare two numbers. One from the existing pipeline, that is $10,000 for the equivalent uniform annual cost. And then $8,000, a little over $8,000 from the new pipeline. Because the equivalent uniform annual cost for the new pipeline is less than the $10,000 annual cost of the existing pipeline. Excuse me. So the new pipeline should be constructed, right? So in B, because the EUAC equivalent uniform annual cost of the new pipeline is less than the $10,000 annual cost of the existing pipeline. So the new pipeline should be constructed. Sorry, it's too small. So what I've written down here is because the equivalent uniform annual cost for the new pipeline is less than $10,000 annual cost of existing pipeline. So the new pipeline should be constructed. Okay. This is the problem 6-37. Okay, and the next problem that we are going to solve is problem number 6-43. Two possible routes for a pipeline. So under study, data on the routes are as follows. If 7% of interest rate is used, should the pipeline be routed around the lake or under the lake? So if the pipeline is routed around the lake, the total length would be 15 kilometers. If the pipeline is routed under the lake, the total length would be 5 kilometers. And the first cost, so $5,000 per kilometer for the around the lake, and $25,000 per kilometer for the under the lake. And the useful life and the maintenance cost is $200 per kilometer per year for the around the lake and $400 per kilometer per year for the under the lake. And the useful lives are both 15 years. And the service values are $3,000 per kilometers and $5,000 per kilometers. And yearly power loss is $500 per kilometer for both of them, both of cases. And annual property taxes are both 2% of first cost. Okay, so you are working on problem number 6-43. For the case of around the lake, that is, if the power line is routed around the lake, how much do you need to spend for the first cost? How much do you need for the how much do you need to spend for the first cost? That's going to be $75,000. Why is that? Because the total length is 15 kilometers, and the first cost is $5,000 per kilometer. So you need to multiply these two numbers. Then you will get $75,000. Okay, 15 times 5,000 becomes 75,000. Then how about the maintenance cost? That's going to be $3,000 per year. Why is that? Because it's going to take $200 per kilometer per hour, and the total length is 15 kilometers. So again, you need to multiply these two numbers, 15 kilometer times $200 per kilometer per year. Then you will end up with $3,000 per year. Likewise, the yearly power loss would be $7,500 per year. Which is from $500 per kilometer times 15 kilometers, which becomes $7,500 per year. And annual property tax. How much is that? It's going to be $1,500 per year. Because this amount is the 2% of the first cost. The first cost is $75,000. So 2% of $75,000 would be $1,500. So $1,500 per year would be the annual property tax. And how about the service value? Service value is $45,000. So again, you need to multiply $3,000 per kilometer times 15 kilometer, which becomes $45,000. That is going to be your service value. So if the power line is routed around the lake, we can draw the cash flow diagram based on this information. Okay? So the first cost is $75,000, and over the next 15 years of useful life, zero, 1, 2 to 15, there is an annual cost of how much? Well, let me redraw the cash flow diagram because it's not very clear. So first we need to consider the first cost of $75,000 and over the next 15 years, there is an annual cost of how much? $12,000. How did you get this $12,000? If you combine all these three numbers, $3,000 per year plus $7,500 per year plus $1,500 per year. If you combine all these three numbers, it becomes $12,000. Okay? That is going to be the annual cost. Okay? And at the end of the 15 years, there is a service value of $45,000. Okay? So if the pipeline is routed around the lake, the cash flow diagram would be like this. Okay? So we can compute equivalent uniform annual cost of this plan. So first you need to convert $75,000 to equivalent uniform annual cost. So 75,000 times A given P, and 7% over 15 years, plus uniform annual cost of $12,000. So simply add this number. However, you need to consider the salvage values at the end of 15 years. Salvage value would be negative cost. So negative 45,000, but you need to convert this salvage value to equivalent uniform annual cost. So again, you need to multiply by this time A given F, right? 7% over 15 years. So if you compute this number, then you will get the equivalent uniform annual cost for the case of around the lake. So 7% of interest rates is given in page number 610 of our text. A given P over 15 periods is 0.1098. This is 0.1098. And what about this? A given F over 15 periods is 0.0398. 0.0398. Okay. So how much is this? Okay, so this number should be $18,444. Okay, so if the power line is routed around the lake, then equivalent uniform annual cost would be $18,444. If the power line is routed under the lake, then how much do you need to spend for the first cost? That is going to be $125,000. How do you get this number? Because the total length would be 5 kilometers, and the first cost is $25,000 per kilometer. So you need to multiply these two numbers. 5 times $25,000 becomes $125,000. How about the maintenance cost? That's going to be $2,000 per year. Again, you need to multiply $400 per kilometer per year times 5 kilometers. 5 times 400 becomes 2,000. Okay. Likewise, the yearly power loss would be $2,500 per year. Again, 5,000 times 5 becomes 2,500. No, here 500. Sorry, the yearly power loss would be $500 per kilometer. So you need to multiply by 5 kilometers, becomes $2,500 per year. And annual property tax that's going to be 2% of the first cost. 2% of $125,000 would be $2,500 per year. Okay? And lastly, the service value at the end of 15 years would be $25,000. Again, the number comes from $5,000 per kilometer times 5 kilometers, which becomes $25,000. Okay? So based on all this information, we can draw the cash flow diagram. If the power line is under the lake. Okay? So we need to consider the first cost of $125,000 for the next 15 years. There is an annual cost of $7,000 are required, because if you consider all these three components, if you combine all these three numbers, $2,000, $2,500, $2,500, it becomes $7,000. Okay? And at the end of 15 years, there is a service value of $25,000. Okay? So this is the cash flow diagram. If the power line is routed under the lake, so we can compute the equivalent uniform annual cost for this case. First, the first cost, $125,000, should be converted to the equivalent uniform annual cost. So you need to multiply by A given P, 7% over 15 years. And then simply add annual cost of $7,000, but minus $25,000, because that would be your benefit. Benefit is negative cost, so you need to subtract by $25,000. But this number, $25,000, should be converted to equivalent uniform annual cost. So you need to multiply by A given F, 7% over 15 periods. So what is these numbers? A given P over 15 periods is 0.1098. 0.1098. How about this? A given F over 15 periods is 0.0398. 0.0398. So how much is this? that is $19,730. So what is your suggestion? If you compare these two numbers, $18,444, this is the equivalent uniform annual cost if the pipeline is routed around the lake. And if the pipeline is routed under the lake, it will cost you $19,730. So definitely the power line should be routed around the lake. In that case, it will cost you only $18,444. Okay. Okay, so this is the problem number 6-43. Okay, I'm going to stop here for today. And I think we need to spend one more hour to solve end of chapter 6 problems. After that, we're going to move on to the next chapter, chapter 7. Okay. So I will see you next time. Thank you very much. Bye-bye.